Okay, so today we're going to talk about confidence intervals for the mean. Last time we did confidence intervals for the proportion, and now we're moving on to the mean. The confidence intervals for the mean are going to use some different formulas from the same formula sheet that we've been using, this reference sheet. We're going to be talking about these two and this one. Similar to the ones above, this formula where it says N is a how many question, and this is the kind of notes that you're allowed to put on the reference sheet, or sample size. Might even say minimum sample size. So the question is about what sample size that we need, and N is always our sample size in these problems. Then we're going to look at these two. These two are very similar to each other. There's just a difference in what they call a critical value. Which is either Z or T. Just a reminder, I am recording this, so we can keep the sound to a minimum, please. Definitely ask questions if you want this. All right. So, I'm going to start with a problem in which we are finding N. Okay, it's a how many question. Yes, we are going to find a sample size. So, there's the formula. And here's the problem. How many cars must be randomly selected and tested in order to estimate the mean braking distance of registered cars in the United States? Okay, we want a 99% confidence that the sample mean is within 2 feet of the population mean, and the population standard deviation is known to be 7 feet. All right, we need to identify some of the parts that are going on in this problem. First of all, because it starts off with a how many question, we know we're doing that formula with N. So we're solving for N this time. Then we need to get all of these numbers, these variables filled out. So as we're reading along, again, we know that we want a 99% confidence level. So 99% confidence level, we'll go to the table, and at the top we have our confidence level, C, 99%, then all the way down to the bottom. 2.576 then is the Z that we need for 99%. So Z is going to equal 2.576. All right, the next thing we need as we're reading along, the sample mean is within. That's a key word, that word within. That word within is a key word showing us what the value E is, or the margin of error. E is the margin of error. Sometimes they'll actually say margin of error, and then you know it's E. But most of the time they're going to use that word within to get that. So E in this problem is just 2, or 2 feet. And they give us that the population standard deviation, also known as sigma, this is the population standard deviation, is known to be 7 feet, so that equals 7. So we have everything we need now just to do this calculation. So N equals, and we'll have multiplication, 2.576 times 7 divided by 2, and then the whole thing is going to be raised to the second power. Don't forget that. Most common error is forgetting that squaring part of it. All right, just going to do this real quick on the calculator. 2.576 7 divided by 2 squared. This equals 81.28. We round, always round up. Always round up, so 82 cars. In order to get a 99% confidence interval, we need to randomly select 82 cars. That's not that many, considering that we're talking about all the cars in the United States. And I think it's because this width compared to the standard deviation is pretty big. If we had a smaller width, then this number on the bottom will be smaller, and we'd be dividing by a much smaller number, and therefore that would be a much bigger number. So the fact that it's only 82 is probably pretty good if we were actually going to have to go randomly select these cars, because that would be costly. Sometimes that process can be costly, and to keep those costs down, that's why we do this little calculation. I doubt that. No, it's not like music or art or something or film. These things came from a long time ago. The guy who, one of the guys who started the statistics, his name is Fisher, and he died a long time ago. But he was a Englishman. All right. Anyway, so we'll do another one. Failure times. Okay. How many? There's our keyword. How many integrated circuits must be randomly selected and tested for time to failure in order to estimate the mean time to failure? Okay. We want a 95% confidence that the sample mean is within 2 hours of the population mean. And the population standard deviation is known to be 18.6 hours. So these are some kind of technical circuits that go into computers or some other very important thing, but they fail. They fail pretty often, and so somebody has to be there on the spot to replace them. This happens a lot of times in the high tech industry, where things are being used over and over and over again 24/7, and so somebody's got to be there to fix things. So these apparently have a standard deviation of the 18.6 hours, but we're going to do the calculation for a margin of error within 2 hours. Okay. Well, let's first talk about what 95% means. Anybody know what that means offhand? 1.9. Very good. Yes, like I said, after a while you get to where you know what these numbers are. Of course, the next chapter we're going to just change that up some. Of course. All right, so our E this time is also 2, just like it was before, but that was 2 feet. This is 2 hours. And our standard deviation is 18.6. So again, N will equal 1.96 times 18.6 divided by 2, quantity squared. I don't know how you guess at that. So maybe you didn't do the square part because it was 18. It was 18, about 18, and then you square it and it's 332. All right, so or 333 because we are going to round this up. Remember, it's always up regardless of what that decimal is. It could be 0.01 and we round up. We just want to make sure that we have enough in our sample to get to that within 2 hours of the population. I'm doing these first because these are the first problems you have to do in your exercises today. Yeah, so they do the ends first. All right, now we're ready to actually talk about confidence intervals. Now, like I said before, we've done confidence intervals for the proportion, and they behave in a similar way in that you take a sample statistic, in this case X bar, and you add and subtract a margin of error. But as you can see, the letters are completely different. Okay, the values are different. We are now dealing with a mean, and we are going to use different values to find that margin of error. So you are allowed to use these reference sheets all the time. Well, you should use the reference sheets all the time. Okay, but it's important that when we have a test on this, there are all 3 different kinds here. You're going to have to be able to determine which one you're using based on what's going on in the problem. Okay, so this first one that we're going to use is it's based on 2 things: the fact that it's the mean and that N is going to be larger than 30. When N is larger than 30, and that's something you have to think about, in your problem, whether n is bigger than 30 or not, then we can use this margin of error that I've taken apart here. And as I say, the first thing you want to do is calculate that margin of error. You want to find out what E is first. Along with that is that your Z test, your Z critical value. Okay, these things are called different things in different topics. So sometimes I say the wrong words. Critical value. RZ is a critical value. On the reference sheet, I use a little star there to indicate that it's a critical value, but you aren't going to see that star in the textbook, so I decided to just drop it here for the conversation. It's still Z, and it still comes from the same place. Okay, we'll address how to get there. It's just the same thing. We're going to use the same confidence interval all the way down to Z at the bottom. So we may use some familiar ones. As a matter of fact, our first example is going to have a 95. And then once you've determined what Z is and you pull these numbers out of the problem, then you could do the calculation. Once you determine what E is, it's just a matter of adding and subtracting it from whatever the sample mean is. Okay? A lot of these things have to be given to you. They're in the problem. They have to be given in the problem, or you can't do the problem. Okay, so let's look at an example. The length of time to earn bachelor's degrees. In a study of the length of time that students require to earn a bachelor's degree, 80 students are randomly selected, and they are found to have a mean of 4.8 years. And it tells you where that comes from. Assuming that the standard deviation is 2.2 years, we are going to construct the 95% confidence interval for the population mean. Does the resulting confidence interval contradict the fact that 39% of students earn their bachelor degrees in 4 years? Okay, so I'm going to leave this last question for later, okay, because our confidence interval is going to kind of answer that question. But the first thing that we're going to do, and you know that when you have these questions, that sometimes there's multiple things they want you to do within the question. Okay, so the first thing that we're going to do is create this confidence interval. There it is. There's the direct. Construct the confidence interval. So that means we have to do this math to create the confidence interval. All right. So what is Z for 95%? 1.96 for now. It's going to change in a minute. Okay. Then we need, looking back at the formula again, we've got our Z. We need our standard deviation. That means that sigma. It means the standard deviation. And that was given to us with the same symbol there as 2.2. Then we need N, which is the number in the sample. Okay, so we're given N this time, and that's these 80 students. We are also going to need X bar. And X bar is the 80 students and their mean. Okay, X bar is the sample mean. We don't need this until the end of the problem, but I'm going ahead and write that down. We need X bar. 80 students. Okay, so we're going to find our margin of error first. I'm just going to rewrite the formula here, which is Z times, and you know, because of order of operations, we can do the multiplication on the top and then do the division. So even though it looks like this in the formula, we can actually do it this way. So this is 1.96 times 2.2 divided by the square root of 80. Okay, and because we're doing this all at once on the calculator, the procedure will look like 1.96 times 2.2. I can go ahead and do the division, open up the square root, and put the 80 in, close the square root, hit enter. So our margin of error is 0.482. I like 3 decimal places where I can. 0.482 is our margin of error. So now we're going to add and subtract that margin of error to X bar. X bar is 4.8. I like to do the subtraction first. So 4.8 minus 0.482 be careful of those decimals, and 4.8 plus 0.482. Let's get these two values. And the lower one is 4.32. Now I'm rounding because I'm at the end of the problem. And 5.28. Now, again, these are years of college before getting a bachelor's degree. So these are years. You can state this as 4.32, comma 5.28. That's what the interval looks like. It also might look like 4.32 is less than the mean this time, mu, which is less than 5.28. And again, these are years. Yes, either one of these would be correct. It's just that, especially when you're in a multiple choice situation, you need to recognize both of them. Paul?
Can you still use the parentheses for this at the end?
Yes, you can use the parentheses.
And, did we do an equation like this?
Yeah, on Monday I introduced the confidence interval for the proportion, and this part of it is very close. I mean, it's just the formulas that are slightly different. Okay, so it's reading the problem and understanding which one of those formulas you need to use to do this confidence interval. So last time I talked about what to do when they say to interpret the confidence interval. This will be interpreted as, with 95% confidence, the number of years it takes for students to earn a bachelor's degree falls between 4.32 and 5.28 years. Okay, but that's not what the question is. This question says, this question that they are now posing after you created your confidence interval, does the resulting confidence interval contradict the fact that 39% of students earn their bachelor's degrees in 4 years? And that's kind of a little thing to think about there. Yes?
Does the point, like the 4.32, does that mean like the months and 4 days?
Yes. Yes.
Okay.
It's 4 years and 0.32 years, whatever that means. So I guess within a year there's 365 days. You could go 0.32 times 365, I suppose, to know how many years and days it would be. Yeah. That's just giving you a general idea. Okay, so these often these decimal numbers are not very accurate. So what this is really saying is that it's a little over 4 years. So this interval is all over the 4 years that they're asking the question about. However, they say that only, and really they didn't use the word only, but only 39% of students earn their degree in 4 years. Okay, since this is less than half, since this is considerably less than probably what it should be, then I'm saying that this interval supports this fact, because really very few students actually get their degree in that 4 years, and this interval is saying, yeah, it's more than 4 years. That's what this interval is saying, that it's more than 4 years, with 95% confidence that the average student, typical student, will earn their bachelor's degree in 4 years, 4 to 5 years, not a little more than 4 years, not exactly 4. Okay, so because that 4 that they're talking about here does not fall in the interval, then that makes this supporting that statement, because only 39%. So really, it's going to take you more than 4 years to get out of college, is what they're saying. And I have 3 adults, children, and all 3 of them took more than 4 years to get out of college.
Even with summer classes?
Yes, for some of them. Different circumstances for each one of them, too. So it took me more than 4 years to get out of bachelor's degree. So it just is very unusual for somebody to actually take those 4 years, just the 4 years. All right, now we're going to talk about ages of motorcyclists killed in crashes. Yes. Well, I know it's an unfortunate thing, and I unfortunately know two people that were my son's age. My son just turned 30. His age that died in the past 10 years in motorcycle accidents, and it's like really. One was going too fast, clearly going too fast for the circumstances, and the other we really don't know what happened. He was actually he was a math teacher at Sandalwood High School, so I knew him that way too. But he played baseball with my son all his life. Went to school with my son, and he was riding a scooter, and he was nobody witnessed the accident, and it was just a scooter leaving school. I think he even had a helmet on, but maybe he didn't have a helmet on. I'm not sure. But anyway, the scooter he lost control of it somehow. You know, people suspect that maybe he was avoiding an animal or something. Yeah, and he went sideways and head hit the curb, and they couldn't bring that brain back. Just couldn't bring it back. It was very sad. It was very sad. And his students were it was a long time before those kids got over that, understandably. Okay, so motorcyclists killed in crash. Be careful if you're going to ride a motorcycle. Be very, very careful, because other cars don't pay attention to you. They miss the fact that you're there. All right, a study of the ages of motorcyclists killed in crashes involves the random selection of 150 drivers. What letter is that? That is N. N equals 150. Okay. With a mean of 37.1 years. Okay, so that's a pretty older age than what I was talking about. So X bar, that's the mean, 37.1. Assuming a standard deviation of 12 years, now that's a big standard deviation, I have to say. Construct the 99% confidence interval for the mean age of all motorcyclists killed in crashes. If the confidence interval limits do not include ages below 20 years, does it mean that motorcyclists under 20 years rarely die in crashes? Okay, so once again, I'm going to address that question after we get that interval made. What's the 99%?
2.57.
So Z equals 2.576. All right, here we go. We need a margin of error. The formula for the margin of error is Z times sigma divided by the square root of N. So 2.576 times 12 divided by the square root of 150. Now, I'm thinking a minute. You just kind of think ahead. I could see that the square root of 150, square root of 144 is 12, right?
Yeah.
And I got a 12 up here. This is going to cancel out. So that number right there is going to be very close to what the answer is. You like to do things in your head, Esteban?
Yeah.
Yeah. That's what I see there. And the answer, the margin of error, is 2.523. That's 4. So how close was that? That's amazing. All right, so I'm going to use 2.52 as my margin of error. So I'm rounding that to 2.52. Now we take X bar, which is 37.1, subtract 2.52, 37.1, add 2.52 to get our actual interval. I totally did something wrong there. It's good when you can see that you did something wrong, too. So we get as the lower value 34 0.58, and the higher value, 39.62. So our interval in years, 34.58 years. And this is the age of these motorcyclists who have died in a motorcycle accident. And 39.62 years. So, you know, almost 35 to 40 is what we're saying the average age is. Because these are ages, years. All right, let's go back to that question. It says, if the confidence interval limits, the 35 to 40 here, do not include ages below 20 years, does it mean that motorcyclists under the age of 20 rarely die in crashes? Yep, I think that supports that statement, because that average age, even with 95% confidence, no, 99% confidence, we're sure that the average age overall falls between 35 and 40 years. So yeah, we're saying that the 20-year-olds are less likely to be in that confidence interval. Do you think 20-year-olds are then safer drivers?
No.
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 What is it really then?
They don't have that
20-year-olds don't have motorcycles, yeah. They're older when they buy those motorcycles.
They're like 26.
Sorry.
26, 25.
Yeah, they're much older than you know, the 20 years that they're talking about. So 20-year-olds do rarely die in crashes, but it's because they don't have motorcycles. Because they're at that age, then their parents are supporting them, and their parents aren't going to buy them a motorcycle. All right, let's talk about birth weights of babies. All right, and this one's got a question you're going to find funny too. Different kind of question going with this. Okay, a random sample of birth weights of 186 babies has a mean of 3,103 grams. And I'll be honest, I don't know what that is in pounds and ounces. And a standard deviation of 696 grams. These babies were born to mothers who did not use cocaine during their pregnancies.
Well, that's a plus.
Yes, that's a plus for those babies, absolutely. All right, then it asks the question, what is the best point estimate? I wanted to put that in there because that point estimate thing comes up over and over again. And what I want you to just understand is the point estimate is the sample statistic out of the problem. And the sample statistic in this problem is X bar, and it's that 3,103 grams.
Is this the other equation?
No, it's not a different equation here. This is just pointing out what the best point estimate is. So they're just calling the sample statistic a point estimate here. That's all they're doing, and so the best point estimate is X bar, which equals 3,103 grams. And you just pull that out of the problem. I just want you to get used to that language that they're using. So they're just substituting best point estimate for the sample statistic. Last class it was P hat was the best point estimate for the proportion. Okay, and now we'll construct the interval and answer their question. So we're going to construct a 95% confidence interval, and we're going to compare the results to this interval, which is the birth weight of babies born to mothers who used cocaine during pregnancy. Okay, so let's do that 95% confidence interval. We have a N equals 186 babies. X bar is the 3,103. Standard deviation here is 696. And remember, this is all in grams. And what else do we need? Oh, yeah, the confidence level, Z will be 1.96. Okay, finding our margin of error first, 1.96 times 696 divided by 186. Square root of 186. which is close to 14. Okay. 1.96.
Do they say 200?
Hundred. We'll go with E equals just 100, and that's grams, 100 grams. So our interval will be the 3103 minus 100 grams. I can do that one in my head. And 3103 plus 100 grams, 203. And these are grams. So the confidence interval, 3003, 3203, is for babies whose mothers do not use cocaine during their pregnancy. And then they ask us to compare that to this interval up here, which is, I'm going to put it to the left because I'll put it in a different color as well. 2608 and 2792.
Yeah, that's good.
So these are the babies whose mothers use cocaine during pregnancy. So the question is, does it appear that cocaine use affects birth weight?
Yes.
Yes, because this birth weight is so much lower in grams than the babies without that exposure.
So ladies don't do cocaine.
There you go. Nobody does. So one of the reasons that I choose these problems is just to get you to see the use of statistics and how it can answer some interesting questions sometimes. All right, we now have to look at what happens when we have an N that is not 30. It is less than 30. It's a small sample. When N is less than 30, we consider that to be a small sample. And it changes our confidence level. That's what it changes the most. We are now going to use, instead of Z, we're going to use a T distribution. So the T is what we need this table for. So T changes things. Let's take a look at the table real quick. We have the same level of confidence at the top here. This whole table is called a T distribution table, and this is where it's going to come into play for this T distribution. To the left here, this column of numbers, it goes from 1 to 29, and then it has the infinity symbol, which is where I've put Z. We've been using this numbers bigger than 30 or higher. We've been using these values at the bottom for Z. Okay, so it stopped at 29 for a reason. Instead of, when we have a small sample, instead of going all the way to the bottom, to the Z, we are now going to have to pick one of these numbers to go down to and stop and have a difference. See how they're slightly different than what's at the very bottom? So we'll have a different value for our critical value. It's going to be called critical value T now.
Can it be bigger?
It might be bigger or smaller. Well, notice that they're all a bit bigger than the bottom here. Okay, but they're different for each level. These levels are determined. This is, see where it says DF. DF stands for degrees of freedom. Something you don't need to know. Why? But degrees of freedom are determined simply by going in a given value minus 1. N minus 1 are our degrees of freedom. So for that's an important idea here. So once you know that your N is less than 30, one of the first things you need to do is figure out what N minus 1 is. Okay, figure that out. You know, super simple, but it's an acknowledgement that you are no longer using a high sample size. when you determine that n equals, n minus 1 equals. All right, so I'm going to play around with the table first. Okay, we're going to see what t we're using. So instead of a z, we have a t now. We're finding a t critical value. So let's all go to the table. Let's see, we're at 95%. N equals 12, so what does n minus 1 equal? 11. So we're going to go over to 11 and go under the 95%, and let's see if everybody could get 2.201. Okay, 2.201 is the test statistic that we're going to use for 95% instead of 1.96. It's a bigger number, much bigger in terms of statistics. So definitely a different number producing a totally different answer. So something you have to be very careful about anytime that n is less than 30. Okay, and this next one, 99%. I'm going to go ahead and remind you n minus 1 equals 14. So we're looking at row 14 under 99%. Row 14 under 99% is 2.977. Okay, there you go. So this is just a little practice on this. This actually came from the textbook. I didn't assign you to do this because I figured I'd show you how. And then you're going to have to do it within the problems that you do. Okay, so 99%, n minus 1 equals 3. So 99%, row 3, 5.841. So that's huge. So that's instead of using 2.576, we're using 5 point something. Okay, again, 95% for n equals 50. Okay, so that one just got thrown in there. I wonder why. There's not a 50 on this table. If there's not if it's higher than the highest number up here, then it's just a z. It's not a t anymore. It's a z. As soon as it gets over 30, it's no longer a t. It's a z. So this is just z equals 1.96. So when the problems start to get mixed up, that is in terms of different sections start to get mixed together, okay, this determination whether n is less than 30 or not becomes very important. That determines whether you're choosing a z or t critical value. Yes?
So for the next one, would it be the
same thing, except it's 90%. So z is going to equal, at the bottom there, 1.645. So as soon as you get an n greater than 30, it's really a z. All right, a couple of 98%. N minus 1 equals 15. So this is definitely a t. We go to row 15 under 98%. 2.602. And then again with the 98% at row 17. 2.567. And then the last one is at n equals 33, so really it's a z, and we've already done 90%, so it's still 1.645. So it's all about determining whether n is greater than or equal to 30, or less than 30. All right, a couple of examples. I know my time is going here. All right, a text messaging question. A telecommunications company wants to estimate the mean length of time in minutes that 18 to 24-year-olds spend text messaging each day. In a random sample of 27 18 to 24-year-olds, the mean length of time spent text messaging was 29 minutes. From past studies, the company assumes that sigma, or the standard deviation, is 4.5 minutes, and that the population time is normally distributed. Construct the 90% confidence interval. All right, let's pull out everything that we need. N equals 27. As soon as you get an N that's less than 30, go ahead and calculate N minus 1, so you're acknowledging that it's a T distribution. I'm going to go ahead and get the 90% T. So T is going to equal what? Okay, so you went to 90% and down to 26, 1.706. The X bar here was the 29 minutes, and the sigma is 4.5. All right, margin of error first. 1.706 times 4.5 divided by the square root of 27.
Where did you get 27 from? I thought it was 29.
And the N was, okay, I'm sorry, N was 26, 27, so this should be 26. Yes. No, it's still N. Oh my goodness, y'all are confusing me. All right, it's still 27. We only use the N minus 1 to find the T.
No, but
Yeah,
how did you get 27 from? I thought it was 29 minutes.
No, it's 29 minutes, but it was, oh, okay, this is N. This is the 27 people.
Oh, okay. Gotcha.
All right, yes, very important. I see. Okay. Yeah, all these numbers are similar. I see the confusion. Even got me there. Okay. But I'm glad you're paying attention. You've got to be very careful. Okay, I'll go with 1.48. Rounding that. That's our margin of error that we're going to add and subtract to X bar. So it really isn't very much here that we're changing this average 29 minutes. All right, so we'll go 29 minus 1.48 and 29 plus 1.48. These are minutes. Okay. So the confidence interval here, with 90% confidence, we are sure that 18 to 24-year-olds spend on average between 27.52 minutes and 30.48 minutes texting each day. It's not. I guess it's depending on how quickly you type and how short your messages are. Could be a lot of messages. I don't know. I was so glad when unlimited texting became available. No, not for me. I'm talking about my kids. One of mine, I almost hate to say this, but she's still on my plan. I'm still paying for her. Oh well. That's
love right there.
it is. I guess so. Yeah. It is tough. It's not nearly as easy as they say, and she's one of those college graduates that had a job for 5 minutes after she graduated, and then now she doesn't have a job related to the field that she graduated in.
Are you still recording?
I am. I know. If you go to the last one, I don't know, she's just on my mind. If you go to the last recording I did, I talk about her boyfriend, so there you go.
You learn so much.
Yeah. All right.
That's so funny.
All right. I think that's enough. I tell you, you got to be careful when you get to these problems because it does change with the value of N being less than 30. But I think I've gone pretty long here with this recording, almost 45 minutes, so that was a long recording. Thank you, guys.
All my notes are